So I'm going to talk about some of our efforts within our group to use machine learning tools for how to extract more information from remote sensing, particularly in the context of data assimilation. So I want to acknowledge the people who've done all the real work, Gautam Panapala and Sharia Ahmed, and also want to acknowledge contributions from Clara Draper and Rolf Reichley on this. So to kind of set the context of premise for some of this work, and as Tristan was talking about, from our last workshop, there was lots of discussion about challenges in land data assimilations, and some of us are focusing on writing these up. And among the many challenges, one of the themes that have come out, which we all know, is the fact that our models and retrieval products often lack the sort of the physical realism, and the fact that systematic errors are dominant in land surface and hydrology models and observations is a big issue in not just the model, but also in data assimilation systems. So largely we get around this issue by focusing on the relative biases between the models and retrieval products, but it's challenging to really address the real systematic errors that exist in the models and observations. And so the question here is, can we use machine learning to help with this regard? So I'll first focus on the observation side of things, using snow as an example. As we know, we've had close to 3 decades of remote sensing measurements from microwave sensors, and I would argue that but we haven't been able to show data assimilation studies that or any other studies that show significant utility for these measurements. If you look at some of the papers, this is the Andreadis and my paper that looked at assimilating AMSRE data, and a little more recently, Gabriel et al., we focused on looking at using these microwave sensors based data for assimilation. And these most of these studies point fault at the observation itself, that they really lack accuracy, and they don't have the interannual variability and to really make an impact in data assimilation. So why is that? I mean, there's little success, I would argue, in using microwave-based sensors, mainly because the lack of skill in these retrievals. So if you look at the retrieval approaches that I use, this is the Kelly et al. Algorithm that's used in for producing retrievals of AMSR-E and AMSR-2. You can see that it's fairly simple. It's essentially a linear regression approach, which is highly parameterized, and it works well over places where this was developed. But you can see that the simplicity of this approach is highly unlikely to be useful in large-scale applications of the algorithm at a global or continental scale. These simple approaches are inherently likely to be limited in capturing the significant heterogeneity and complexity of snow that exists. So folks have tried to get around this also by using machine learning approaches as observation operators to work directly with microwave radiances. But again, these methods have also shown little utility, but that primarily is because of the fact that you're trying to, these approaches use machine learning as a statistical fit between essentially your imperfect model and satellite measurements. So that notion of physical realism through ground observations, that's not really introduced in these methods. So that's something we try to address by essentially, it's a very simple approach by trying to see if we can generate a better statistical fit with machine learning. So in this case, we use deep learning models. The approach is to use multi-frequency microwave observations or channel brightness temperature observation from AMSA2, and essentially train it to in situ information using a two-dimensional convolutional neural network. So overall, the approach is simple. Some of the challenges of using these approaches comes with because of the fact that there is spatial and temporal gaps in our remote sensing measurements. So convolutional neural networks are typically used a lot for image classification or image analysis, and typically, even if gaps exist, they are temporally invariant. So remote sensing and in situ measurements, the gaps they keep changing all the time. So that was some of the difficulties that we had to overcome. And essentially, we have an approach where we train these brightness temperature observations to in situ measurements. And here we don't prescribe any notions of sensitivity or which channels are important. So let's see if the algorithm can sort of figure it out. And the results were somewhat encouraging. So first is to see whether we can outperform the standard retrievals. And not surprisingly, we see that the machine learning algorithm does a lot better than those simple empirical approach-based retrieval approaches. So this is comparing the performance of the machine learning based product to ground measurements. Again, I want to emphasize here that the training and the testing is completely independent. So we present a portion of the available data to the machine learning algorithm for training, and then the remaining data is used for evaluation. So the correlations are fairly good with low biases, and RMSEs are also low. So if you look at the bottom row, which shows the CDF of these measures, correlation, bias, and RMSE, the light blue shows the standard retrieval, and we also here used another product from University of Arizona, which is a gridded product that was developed by through a temperature index model to using in situ measurement. So assuming UA is a fairly good product, we see that the machine learning approach, at least the PDFs, are fairly close to the UA product and much better than the standard retrievals. And another question is to see if these algorithms can address some of the known deficiencies of microwave sensors. So the standard approach does fairly poor over deep snow and over forest areas. And the idea here is to see if the statistical fit introduced by the machine learning algorithm does better. And it was also an encouraging result. So on the left here shows the performance of the algorithm over high elevation terrain. The black line is the observation, and then the machine learning algorithm does fairly well compared to those observations, particularly over deep terrain. And then the middle plot shows the correlations for the standard retrieval, and the solid lines show the melt season, and the dashed lines show the performance during the deep snow or the peak winter season. So again, this is encouraging in that the machine learning algorithm seems to do pretty well compared to UA, University of Arizona dataset performance during both the melt as well as the deep snow season. This is during the melt also is a period where the microwave based retrievals are documented to struggle. And finally, the third one, which is focused over the forested areas. Again, if you focus on the three sets of plots, one for AMSA2, which shows the poorest skill, and then the machine learning algorithm does much better and getting closer to the UA performance over these more dense forest type of areas. So the question is, is this doing a pure statistical fit? Are we learning anything from these? So the encouraging thing is that we can infer more physical information from the deep learning approach itself. So what here I'm showing is an estimate of the importances of different channel information that's used in the machine learning algorithm. This was developed during the peak snow time periods. So again, we are not prescribing a certain difference relationship as it's used in standard approaches. The algorithm seems to infer a different levels of sensitivity for these channels. And if you look at the spatial map, it also shows that this is not a random pattern. There is a certain spatial features to these relative importances. And similar maps are also developed for melt time periods and so on. Another thing I want to point out that there is a lot of change. There is sort of sensitivity associated with this, not just spatially, but also in time. This is an example of that, which shows the Shapley values, which is a measure of the relative importance of a certain channel as a function of the brightness temperature. So if you look at, let's say, the 36 gigahertz vertical channel, that sensitivity changes a lot as a function of the temperature. Essentially, that sensitivity decreases as the temperature increases. So this is the point is that that there is these sort of sensitivities are difficult to characterize within a simple retrieval sort of approach, and the machine learning algorithm seems to do a much better job at figuring these out. So the outcome of this exercise is that yes, it seems to be doing better in terms of producing better retrievals. They're not exactly black boxes as they're often termed. They can provide valuable information about the underlying sensitivities, which we can use to improve our retrieval models, or even the notion of how what kind of channels are important for measurement. And if these work, we can use them and turn them around and use them as observation operators within a data assimilation system. So hopefully this is an example of how we can improve the observation side. Now, looking at the models, can we do something similar on the modeling side as well to improve the realism of the model? So we all know that there is a large volume of literature on model calibration efforts in hydrology, relying on all kinds of approaches. And these methods are typically very expensive computationally, and because of that, they become impractical over large domains at fine spatial resolution. And people have used regionalization methods, but they also often lead to suboptimal solution. There was a new, thanks. So there was a new effort by Xiaoping Chen's group using model calibration using a machine learning approach. So we use that within our model to calibrate the NOAA-MP land surface model. The approach is fairly simple. First, we train a soil moisture surrogate model that emulates NOAA-MP. And then because these emulators are very fast, we can use them to learn the underlying parameters, and then transfer these parameters over to the actual land surface model, essentially getting around the limitation of running many iterations of the land model. So this is a quick example. We developed an emulator for the NOAA-MP. The performance is kind of shown here in this time series. And at the bottom, this table shows the computational advantage. Typically, if you want to run NOAA-MP for 3 years, it took about 18 hours. Comparatively, the emulator model took basically a fraction of that amount. And so the performance now, using the emulator model, we can learn these parameters and address the bias. And these box plots show the performance of the surrogate model. Essentially, the bias is reduced significantly, which is what the calibration effort is trying to do. And then once the parameters are developed, we transfer that over to NOAA-MP. So on the left, you can see the default model performance. The middle panel shows the improvement with NOAA-MP. The biases are significantly reduced. I want to caution that this is still sort of an early result in that we only completed three sort of iterations of the model. So we need to run this more for a longer time period to see a better performance. So anyway, I think the one sort of message I want to end with is that we see promise with the use of these models, mainly in terms of improving the realism of retrievals and reduction of systematic errors in models, which can essentially help towards improving the performance of data assimilation systems.